So overview again, first polynomial contrast, then one effect size measure for contrasts, then the comparison between ANOVA and multiple regression in a 2x2 design, then nested effects in a 2x2 design, then an example with a 2x3 design, and then covariates with ANCOVA and differences between slopes. I'm not sure, depending on your interests and how far we get, we can also skip the 2x3 design and directly go to covariates. I'm not sure exactly, because I think someone asked for moderator analyses. Yeah, so if you want, if you have a different preference than this ordering, just let me know. We can also see later or now. Okay, polynomial contrasts. Sometimes we have factors that are ordered. We had this previously, this discussion that there could be a gradient or some medication that increases in dose, or some difficulty of a word that increases step by step, or difficulty of some stimulus and gets harder and harder. So we learned about different ways to compare individual factor levels in such a setting. Instead, what we can do, we can use polynomial contrasts. For example, we can test whether there's a linear increase, this blue line, that there's a linear increase across all factor levels. So the difference between x1 and x2 would be the same. The assumption would be that the difference between x2 and minus x1 is the same as x3 minus x2 is the same as x4 minus x3. So that there's a linear increase. And this can be tremendously helpful in situations where maybe the experiment does not provide enough power to test simple differences or repeated the sliding difference contrast. So remember, in sliding difference, we compare each two categories separately. But maybe the statistical power is not high enough to get these individual differences significant. What we can do instead, we can just pool all the variance in one linear predictor. And sometimes this is higher power to detect an effect. But we cannot only have a look at linear effects, we can also look at quadratic effects. That's the red line here. You can see, for example, we could have a hypothesis that responses are high on both sides of the factors on the distribution, but are low in the middle. Or shown in orange, we could also have expectations about a cubic effect. That first it goes up, then goes down again, and then goes up, for example. In fact, this is a situation that sometimes happens in research. So in my field, in reading, if you have word frequency levels on the x-axis with low frequency here, high frequency here, we observe that reading fixations are low on very low frequency words. But then there's some cubic effect. There's an increase in frequency in word fixation durations for low frequency for medium frequency words. So just to say, this can sometimes be the case, and you might have hypotheses about it. What is definitely often a useful thing is the linear effect. So we can try to code contrasts for such polynomials ourselves. Or maybe wait a second, let me say, if you have 4 factor levels, the most you can get is the cubic effect. So it's always one less than the number of factor levels. So the linear, you can get a linear effect with 2 conditions, a quadratic with 3 factor levels, and a cubic with 4 factor levels. So how would we set up, how would we define contrasts that test polynomial effects? What we can do is we can just implement a linear effect. This is shown here. So this should we center our predictor. So we make sure the mean of the predictor is 0. That's always a useful thing, because then the intercept, we learned in the previous sessions, then the intercept is the grand mean, and that's desirable in many situations. So here I plotted 3, -1, +1, +3, but to make sure that the differences between these two are just of size 1, divide this by 2. So the linear effect, we can see this down here, is -1.5, -0.5, +0.5, and +1.5. So the difference between 2 neighboring levels is exactly 1, So we can interpret the regression coefficient if you such that if you go from x1 to x2, that the increase is given by the regression coefficient. So how do we code the contrast for the quadratic effect? We just take the linear effect and square it, and then we subtract the mean, because again, we want to have a centered contrast. And for the cubic, we proceed in the same way. We simply compute the linear effect to the power of 3, and then we subtract the mean, which is 0 anyways. And then we here save this as a matrix and assign this to the contrast, and we see the linear effect. We already looked at it. The quadratic effect is 1, -1, -1, and +1 centered, and the cubic effect is -3, -0.125. So it goes. Yeah, we can visualize that in a moment. So now let's fit the model with this contrast matrix. And what we see, let's first look at the last thing. The cubic effect has a positive estimate of 10, and it has a t-value of 3. That's significant. So this is in line with what we see here. So the positive cubic effect goes up on the right and down on the left. So the positive estimate of 10 seems reasonable. How about the quadratic effect? This has a value of 5. This is again positive, also to a t-value of 2.24, 0.04 for the p-value. You can see again the positive quadratic effect, both ends go up. If it's negative, both ends go down. But this seems reasonable, so there's a quadratic effect as well. Now we look at the linear effect, and we see that here the estimate is -12.5. That's strange. The blue line clearly goes up, it doesn't go down. It's not significant, 0.1, but the direction of effect is strange. That shouldn't quite capture it. So why is that? What's going on? Anyone have an idea? Okay, I will show where it comes from. What we can do is we can we can compute the correlation matrix from this contrast matrix, and what we find is that the linear effect and the cubic effect are highly correlated at 0.96. The quadratic effect is not correlated with the linear and not correlated with the cubic. But the linear and cubic effects are highly correlated. Why is that? If we take a look at the quadratic effect, that looks like that. If we imagine a linear line going through, that doesn't seem to have any relation. But here's the cubic effect. If you see a linear effect going through here, it's clear that this is very similar. So the two contrasts nearly measure the same thing. And then this is an issue that we discussed previously, that if you have a highly correlated predictor, the estimates may not be accurate anymore. So here the linear effect suddenly shows a negative sign, which is not what is shown in the data. So what can we do about that? One thing that we can do about it is we can use a predefined function called contrast poly with 4 factor levels, and this has the following contrast coefficients. So we see this is some linear increase here, but we see that the differences are not 1, so the regression coefficients will be hard to interpret. Here's some quadratic effect that's similar to ours, and then the cubic effect, but it's not clear how these numbers really come about. When we plot it, it shows that the cubic effect, if we plot the cubic effect in here, we see that it goes up, goes down, and goes up again, so it overshoots kind of. So we can see that it's not closely associated with the linear increase anymore, okay? And if we look at the contrast coefficients and look at the correlation matrix, you can see that the off diagonals are now 0. So these these contrasts are in fact orthogonal. So that's a good thing. They should not be highly correlated anymore. So this is one thing we can do. If we estimate that, in the model apply. So we assign the contrast matrix to the contrast attribute of the factor, and we estimate the model. The problem is now we see that again the cubic effect has a t-value of 3 and a p-value of 0.001. That's exactly as before. The quadratic effect is also as before, 2.24 and 0.04. That's the same. However, the question is now how to interpret these estimates, because these numbers that were given here are kind of not very straightforward to interpret. It's not that there's a linear effect. So remember that we always, when we have a step of 1 on the predictor variable, then no, that's actually no, forget about that. So these are really kind of strange numbers. So it's not straightforward to interpret these numbers. But if we look at the linear effect, we see that now this is positive. This is what we expect it to be, right? Now there's a positive t-value of 4 and it's significant. So there's clearly a linear increase here. So this is now captured well. However, as I said before, this number is 17.89. It's unclear. It's not quite straightforward how to interpret that. So what does it mean? How many, if I take a step of 1 from x1 to x2, how much do I have to go up? It's not 17. I think that number is not 17 because these differences between the conditions are not 1. So the difference here is rather something like 0.4. So we can compute the numbers and try to figure it out. But the alternative, if we compare this to our self-made contrast, we can see that now the linear effect is good, is positive, but now the numbers are not interpretable anymore. So what can we do? What we can do, we can orthogonalize the self-made polynomial contrasts. So that's something I briefly mentioned previously, that if we have highly correlated predictors, one thing we can do is we can try to orthogonalize them with respect to each other. So what that means is that we take our contrast matrix and that we predict the cubic effect based on the linear effect. Okay, this is just a linear model based on this contrast matrix. So xpol was defined. Where did we define xpol? Sorry. Xpol is this matrix here that we defined at the very beginning. So we have a linear effect, the quadratic effect. This is what we started out with. And we can now make a prediction, a regression of the cubic effect on the linear effect. So we predict the cubic effect based on the linear effect. This is what this model does. And what we can do now, we can take the residuals of this model and store this as the new cubic effect. So this is what it looks like. The linear effect still goes from negative 1.5 to plus 1.5. The quadratic effect hasn't changed, 1 minus 1 minus 1, 1. But the cubic effect now looks very different. These are now the residuals. This is kind of what the cubic effect is when you take out the linear component of it. And we see it's here minus 0.3 plus 0.9, minus 0.9 plus 0.3. It's not, there's no increase or decrease in this anymore. So it's unrelated. So if we now compute the correlation matrix of this contrast, we see now that the off diagonals are all 0. So these contrasts are now not correlated anymore. The 0.9, this correlation of 0.9 something that we saw before between the linear and the cubic effect is gone because we have taken out the whole linear trend from the cubic contrast. Okay, so what happens if so here we apply this to our contrast matrix and now we run the model again. And then we see that the estimate for the cubic effect has not changed. It's still 10 and the same t-value and p-value. The quadratic effect is still 5, same t-value and p-value, but now the linear effect has a value of plus 8. So now we see this increase that we would expect. And we see again the t-value of 4. So this is exactly the same t-value that we also saw in this ready-made polynomial contrast. Here, there's also a value of 4. However, here the the coefficient are better, much better. Sorry for this flipping back and forth. However, the estimate, the regression coefficient, is much more easily interpretable. So it has a value of 8. So if we go from x1 to x2, the line should increase by 8 steps. And we can check whether that's actually the case. We can run the same model, but now we take out the quadratic and the cubic effect by specifying 0 for the contrasts. So all contrasts associated with the cubic and the quadratic effect are 0. Just the linear effect is there. And if we estimate the model, we can see that when we just have a linear effect, that this also has a slope, an estimate of 8, plus 8. So in this plot, when we go one step to the right, we have to increase by 8 units. This tells us that this estimate of the linear effect is in fact accurate. But now, so now we have the same test statistic that we have when we use this predefined function contrast polynomial. However, we have better interpretable estimates. So we can directly use these estimates as a measure of effect size. Okay. Yeah. So therefore, I would recommend manually constructing these contrasts and then residualizing the higher order term by the lower order term. Okay. Yeah, that was the polynomial part, polynomial trends. Let's next discuss an effect size statistic for contrasts. So we have now a situation, we have different contrasts, linear, quadratic, and cubic. What we might be interested in is how big is the contribution of each of these parts. So how big is the contribution of the linear effect? How big is the contribution of the quadratic effect? How big is the contribution of the cubic effect? And to do that, we can look at how sum of squares are computed in a linear model. So this is a short excursion in the realm of ANOVA, in analysis of variance. So the total sum of squares is the total variability in the data. So the square deviations of the data from the mean, that can be computed. So the total sum of squares, remember you have learned this in statistics about analysis of variance. You can subtract the individual data point for the general mean, the grand mean, square that and sum it up for all data points. That's the total sum of square. And the total sum of squares can be partitioned into an effect sum of square and residual sum of square. So total sum of square is effect sum of square plus residuals. In the current case, you can compute this residual sum of square by taking the difference between the individual data point and the predicted value and square that and sum it up across all subjects. The effect sum of square can be computed. So we have the overall mean, and we compute how far does the individual factor level, mu j, deviate from that overall mean, and multiply that by the number of subjects in that condition. We square that value, compute that for every subject, so times the number of subjects, and sum it up across all factor levels. That's the effect sum of square. So this residual sum of square captures how much variability there is in the residuals, and the effect sum of square captures how much variability in the data can be attributed to systematic differences between groups. Now, interestingly, this effect sum of square can be further partitioned in the contributions from each contrast. So we can also compute a sum of square for each contrast, and that's computed as by computing the product of the contrast coefficient times the condition mean, sum this up for across all 4 factor levels, and squared, divided by, and now we square the contrast coefficient divided by the number of subjects in that condition and sum it up across all condition means. So I'm not sure you have to remember this formula, but it tells us the sum of squares for each contrast that we compute. And it turns out that the sum of squares of the effect can be is a sum of all contrasts of all individual contrasts. So this provides a basis for a measure of effect size. We can just compute the percentage of variability of the factor that is explained by one contrast. So that's this one. It's called R alerting square. And you compute that by taking the sum of square that is explained by one contrast and divide it by the effect sum of square. And this tells us if this R square alerting is close to 1 for one contrast, it tells us that this contrast really explains all the effects. So maybe there's just the linear effect. If the R square alerting is low for all of the contrasts, it tells us that the effect of this factor can be explained only by combining all the different contrasts. Okay, let's do it in an example. We use this contrast poly function, assign this to the model, run the model, extract the model matrix. So we have here one factor, but we want to compute the sum of squares for each contrast separately. So we extract the model matrix, the design matrix, and we store the linear, the quadratic, and the cubic covariate. Okay. So now we can run the model again with the. So this is the same. So this is the same model as this one above here with the factor x. But now this factor x has 3 contrasts, linear, quadratic, and cubic, and here we specify them separately, linear, quadratic, and cubic. But otherwise, it's exactly the same model. What we can do now, however, is we can run an ANOVA on this model. And now we can extract the sum of squares. So the sum of squares here indicated for each contrast separately. Here, 1,600, 500, and 900. So we can extract that from the model, 1,600, 500, and 900, can compute the sum of that, and that's the effect sum of square. We said the sum of the individual contrast sum of squares is the effect sum of square. So that's the sum of squares associated with the factor overall. Now we can just divide the sum of square on the individual contrasts by its sum. And what do we find? We find the linear trend explains 50% of the contrast. 20% is explained by the quadratic and 30% by the cubic contrast. And now we can have different situations here. One is called an ecumenical outcome. So this is the case where the primary contrast that's of primary interest, say the linear trend, explains only part of the data. Other structure is in the data. So here we would say linear trend is important, but there's also a substantial cubic effect, right? There could also be a canonical outcome. This would be the case when the primary contrast, for example, the linear trend, explains a large part of the variance associated with the factor, and that no additional structures in the data. So this is a way to look how important our primary hypothesis is for explaining the variances associated with the data. Okay, and now, yeah, we know that all of these play some important role. The linear, but also the cubic effect explains some variance here. Yeah, that is what I wanted to tell you about polynomials and effect size statistics. And now let's turn to a big new chapter. And this is the analysis of designs where you have more than one factor. So here, as an example, where you have a 2x2 design, factor A with 2 levels, factor B with 2 levels. And interestingly, to make some analysis later on, I chose this example by using the exact same data points that we have used before. So this was the pattern we had before, and now we transform it into this one. And we do that simply by assigning these points to different factors. So x1 and x3 can be seen as this red line, and x2 and x4 can be seen as this green line, right? So exactly the same data, just a different way to describe the data. So now let's assume that we have one factor A and we have a factor B, and we want to analyze this data. And let's first start by comparing an ANOVA analysis with f-tests to a multiple regression analysis with contrasts. So let's be naive and just start the analysis. So we can use the AOV function for ANOVA. The dependent variable is explained as a factor A times factor B plus some error for the subjects. And this is the result from the ANOVA analysis. We have an F value of 5 for the interaction, P value of 0.0399. Factor B is highly significant, P value 0.0004, F value of 20. And factor A is just so significant, 0.0399 with the F value of 5. Now let's do the same with the linear model. Again, dependent variable as a function of factor A times B. So we include the interaction and we plot this table. And we can see, so what we know is that an F value with one denominator degree of freedom is simply the t value squared. So if we square the t value, we get the F value. So 2.24 squared is exactly 5. And also we can see the p value is exactly the same for the interaction term. But when we look at the main effects, we can see that these are very different. The factor B had a strong effect here. Here it doesn't have an effect. So 1.5 squared is certainly not 20. And factor A was also significant up here. It's not significant at all. And a t value of 0 squared does not get 5. So what is going on here? Why are we not testing the main effects? So the interaction seems to be fine, but what's going on with the main effects? What it turns out is that if you have a 2x2 design and you want to run you want to get the main effects, you want to get these ANOVA results in the linear model, you have to use some contrasts. So if we assign some contrasts to both factors A and B, and then we run the model, now we can compare the p-values. That's exactly the same for the interaction. And also factor B now is highly significant, 0.0004, and factor A is also the same. And if we square these t values, 2.24 is 5, minus 2.24 is also 5, and minus 4.47 squared is 20. So now we get the same results. Yeah, that's an important point. If you have a 2x2 design and you want to get the main effects and the interactions, you have to use these sum contrasts. Okay, so now what we did so far is we computed we were running a model where we have two factors in our data, in our simulated data, factor A and factor B, and each of them was assigned a separate sum contrast. This gets this sum contrast, this gets this sum contrast. And then we can run a linear model where we specify A times B and we get these results. However, an alternative way that gives a lot of power in the analysis is to use a single contrast matrix for two factors. So a 2x2 design consists of 4 different factor levels, right? 2 times 2 is 4. So 4 different factor levels, and we can code the exact same analysis by having just one design matrix for this 4-level factor. We can actually extract that using a little bit of tidyverse. We can extract the model matrix for A times B from this data, but we do it in a way such that we get each condition only once, each factor level only once, no, each condition. So we can see we have 4 conditions here. The first 2 are A1, and the second 2 correspond to A2. But we can see that they also are associated with B1. So B1, B2, B1, B2. So we can see that these 2 factors describe these 4 factor levels. But now we are not interested so we're assuming that these are 2 factors and not 1. But we can describe them in one matrix. And if we look at the model matrix from this, we said that this A times B gives us the the main effects and the interaction, we can look at what the contrasts look like when we use some contrasts. We first get an effect for A1. That's putting an A1 and a 1 and a -1 and a -1. So A1, wherever there's A1, it gets a +1. When there's an A2, it gets a -1. And then we get a main effect for factor B. This is 1, -1, 1, -1. So B1 is +1 and B2 is -1. Again, +1, -1. And then we get an interaction, A1 times B1. And this is simply the product of A1 times B1. So 1 times 1 is 1. 1 times -1 is -1. -1 times 1 is -1, and -1 times -1 is 1. So we can just multiply the two main effects, and then we get an interaction term. In this model, these are different main effects in the interaction, but we can now assume we can go back to our original data where we have one factor x, not a and b, but one factor x, and we can assign this. We can design one contrast matrix. We can design one contrast matrix that codes these main effects and the interactions. So we can manually, so this is what we saw here, main effect, and interaction, but we can now manually encode this this contrast matrix where we say contrast A as the main effect. So one contrast A is coded 1, 1, -1, -1. We code a contrast B, the main effect for B, 1, -1, 1, 1, -1, and we code the interaction. But now we don't have this as separate contrasts for A and B, but we have it as one common contrast for the factor X with 4 levels. Okay, so this is now our contrast matrix for one 4-level factor. And the nice thing about it, if we run this model, we could see here it gave us -5, -10, and +10 as a result. And we can, if we do this manually, we get also -5, -10, +5. So we get the exact same results. One time we code it as 2 factors, and we compute the interaction manually. And the other time we code it as one contrast matrix. We do the same coding, but we just have one factor with 4 levels and code these main effects interactions manually into the contrast. Is that clear? Now I would like to see your faces, but I hope that's kind of clear what I did here. So we have now one contrast matrix for 2 factors instead of one contrast for each factor. That's a new thing. We can just have one big contrast matrix that codes all effects, even if we have a 2x3 design or a complex design. We can have it all in one big contrast matrix. And this gives us more flexibility, of course. So next, the next thing that is sometimes important in designs with multiple factors is that you have nested effects. So what are nested effects? Nested effects are sometimes also called simple effects. For example, we might be interested in whether there's a difference in this red line. So is there a difference between A1 and A2 for level B1? Or we might be interested in the difference between these 2 green points. So is there a difference between this point and this point? This would be a nested effect. And an example from my field of research could be you have a reading study and there are 2 tasks. So one is reading and the other one is visual search. So you search for a target word, and it is known that in reading, difficult words are longer fixated than easy words, low frequency than high frequency words. So this would be the green line. You would expect a difference depending on verb frequency, verb difficulty. But when you look for a word in a text, you just scan over the text and you don't look in detail, then the word difficulty doesn't matter. This would be the other nested effect. And then you would find overall faster reading in the visual search condition and no effect of word difficulty. Okay, so these are nested effects. So how can we test these? Let's start with the hypotheses. First, we have a hypothesis. We hypothesize that there's a general difference between tasks. So the green line is different from the red line. We compute that by just saying the average. So now we go again in the situation where we code these hypotheses by having a single design matrix for all 4 factor levels. Okay. So we code these hypotheses by looking at this graph at the left, but we intend to test these effects that are shown on the left. Okay, is that clear? Given that the green line is x2 and x4, so we want to test the difference between the red line and the green line. So we take the difference between mu1, we take the average of mu1 plus mu3 divided by 2, mu1 plus mu3 divided by 2, so that's 10. And then we take mu2 and mu4. Mu2 and mu4 are the green line. We take the average of that, it's 30. So the difference is 20, we can already see. And then we code this at the hypothesis. So mu1 gets and mu3 gets a -1/2, and mu2 and mu4 gets a +1/2. And now we can test the hypothesis that the nested hypotheses that we are interested in. We are interested in whether these two red points are equal. So 2 red points are x1 and x3. So mu1 is equal to mu3. We can encode this minus mu1 and +1 mu3. And we are interested in whether the two green points are equal. So whether x and x4 are equal. Mu2 equals to mu4. So we get a minus for the -1 for mu2 and a +1 for mu2 for mu4. Okay, so we can enter this in our analysis. We have the 4 factor levels, x1 to x4. We can see that we have here a main effect. We test the average of x1 to x3, and how this differs from x2 and x4. And then we have these nested hypotheses, nested effects. We want to test the effect of A within B1. A within B1 is the red line. And this is done by comparing That's done by comparing x3 versus x1. And then we want to compare the effect of A within B2. So that's the 2 green points. That's by comparing x4 against x2. And then we can apply the generalized inverse. So this is our hypothesis matrix. We can apply the generalized inverse, and we see that the result is very different, very similar. So the main effect of B is unchanged, and the effect of A of these 2 nested effects is very similar. Actually, I didn't tell you that in advance, but if you have orthogonal contrasts, the generalized matrix inverse is computed on each contrast separately. So you can ignore the other contrasts in the operation. So if they are orthogonal contrasts, they don't influence each other. If they are not orthogonal, then they can have an influence on each other. If you have an orthogonal contrast, the only thing that changes is the scaling. So here I have -1 and +1, you have -1/2 and +1/2. Okay, so the scale changes, but the contrast otherwise stays the same. Okay, now we have this contrast matrix. We can estimate this, assign this to our contrast, and estimate it in the model. So we see that the intercept is again 20. That's the grand mean. We have a difference of factor B of 20. So the average of B2 is 30. It's 20 larger than the average of B1. And now we have these 2 nested effects. So we have the effect of factor A nested in B1. A nested in B1, that's 0. So these 2 points here are completely identical. And we have the effect of A nested in B2. That's the green difference, and that's exactly 20. So 40 and 20, the difference is 20. Okay, so you can test directly these nested effects instead of using main effects and interactions. And you should especially do that. So often you have hypotheses about these nested effects. Often you don't have a hypothesis how this change, that there's an overall, like in the example that I showed you earlier. We don't have an expectation that there's an overall effect of word frequency and that this differs, but we have an effect that this word difficulty has an effect in one task, but not in the other task. Actually, to tell you the full story, there's also an easy way to code nested effects in R syntax. If we go back to our coding as two separate factors, A and factor B, we can code them as effect coding in both examples, so minus 0.5 plus 0.5, and then we can write this B/A. And if you write this B/A, that means that you get the effects of A nested within levels of B. So you get, again, the main effect of B, that is 20, just as above. And now you get the nested main effect of A within B1, that's 0, just as up here. And the nested main effect of within B2, that's 20, just as above here. Okay, so just by using the slash, we can specify this nesting structure in R directly. And of course, we can have the other. We can do the nesting the other way around. Maybe we are not interested in whether there's a difference in the green and the red line. Maybe we are just interested in whether there's a difference between red and green on the left. So this effect, this would be the difference between reading and visual search and search for a target word when there's an easy word. And we could be interested in this difference between these 2 points on the right side. So maybe the difference between tasks, reading versus search, when there's a difficult word. So this is just the other way around. And we can again code our hypothesis matrix, where we first compute the average of x1 and x2 and compare that to the average of the x3 and x4. And then we can specify the one effect of interest is between these 2 points, that x1 and x2. So x2 versus x1. And then we specify the difference between these 2 points. There's x3 and x4. So we specify here minus x3 plus x4. Again, do the generalized inverse operation. And apply this to the factor, run the linear model, and what we can see now is the main effect. The main effect of A is 10. So let's see what the main effect of A should be. Here it's the average is 15. Here the average is 25. The difference is just 10. That's fine. So then we can test the effect of B within A1. A1 is on the left. The effect of B is just 10 on this side. This is exactly right. And we can test the effect of B within A2. The effect of B within A2 is this difference. That's 30. 40 minus 10 is 30. So we get this estimate of 30. Okay, so this works just the other way around. And in R, we can again assign effect coding to the factors. And now we write A/B. So now we get effects of B nested within levels of A. So B1 nested within A1 is 10. So these are just, again, the same results. 20, so 10, 10, 30, 10, 10, 30. It's just exactly the same. So this is an additional possibility when you analyze factorial designs with multiple factors. Sometimes you have hypotheses about these nested effects, and then this provides these nested effects provide a way to test these simple effects instead of doing the 2x2 design, the main effects and the interaction, because sometimes that's where the hypotheses are, and then you shouldn't test hypotheses that you're not interested in, but you can directly test these nested effects in case you have a study where this is what the hypotheses relate to. Okay. Sometimes this can also be used to do useful to do post hoc tests in linear mixed effect models. It's difficult to do simple t-tests for the individual conditions because you have all this random effect structure. So one thing in linear mixed effect models, sometimes you are first interested in the interaction, and then you want to know post hoc whether this effect gets significant and this effect gets significant. And then you can use this nested coding to test in the linear mixed effect model whether this effect is significant as expected and this one is not significant as expected after testing the interaction as well, right? So this provides a way to do post hoc testing for such effects in linear mixed effect models. That's where it's also very useful. Okay, we said before we compared ANOVA, the ANOVA result with for a 2x2 design with the same analysis in linear models using some contrast, and we said that both show the same result, right? So there's no difference. But we also said that if we use treatment contrasts, that suddenly the results differ. The interaction was the same, but the main effects were very different. So the main effect, the p-value here for B is very different, it's not significant. And the effect for A is also significant up here, but not down here. So what's going on? Is this just simply saying that these effects down here are meaningless, or is there a way to understand what they measure? And the second is of course the case. So these test very specific hypotheses, and let's look at how we can understand that. So if there are interactions between contrasts in a design, the general rule is if there's an interaction included in the model, the effect of each factor in the interaction tests its simple effect. It tests its effect at the location 0 of all other factors in the interaction. That's a bit abstract. So if the other factor is coded as a treatment contrast, then the main effect tests the nested effect within the baseline condition of the other factor. Okay, let's get to an example. That's maybe easier than the abstract formulation. Let's say factor B is coded as a treatment contrast, but we are interested in factor A, and there's an interaction between A and B. Then the question is, what does the main effect of factor A test? Factor B is the treatment contrast, but we are now looking at the effect of A. A does not test the main effect, not the average effect. It tests the effect of A nested within the baseline level of B. Okay. This is important. So that's a bit strange, right? What factor A tests depends on on how B is coded. In fact, the effect of factor A is in the condition where B has a 0, and B has a 0 in the baseline condition, and therefore it's the nested effect. A tests actually the effect of A is actually a nested effect within the baseline of B. Then we can do the game the other way around. What if factor A is also coded as a treatment contrast? But now we look at the effect of B. What is the effect that factor B tests? So, well, if we want to understand what B tests, we have to look at factor A. And where is the 0 in the coding of factor A? The 0 in factor A, it's a treatment contrast. The 0 is in the baseline level. So the baseline level of A codes a 0, and therefore the effect of B is nested within the baseline level of A. That's really a bit complicated. But let's look at a concrete example. So again, we have A and B coded as treatment contrasts. And so A1 would be the baseline level of A, and B1 would be the baseline level of B. And now we have this effect of A. Importantly, we have the interaction included, 2 main effects and an interaction, or the main effects of the factors and the interaction. So now we want to understand, we have 2 treatment contrasts. What does this effect of A test? It doesn't test the average effect of A. The average effect of A would be computed by computing the average here. That's 15, 20, and 10 is 15. The average on the right side is 25, and then the difference is 10. But this is not what this A tests. It doesn't have an estimate of 10. It has an estimate of 0. Why that? If we want to understand what A tests, we have to know how B is coded. B is coded as a treatment contrast. So A tests the effect in the baseline level of B. The baseline level of B is B1, so A tests this effect, the nested effect. And this is 0, just as it's written here. Okay, so this is important to know. So if this is especially important because if you don't think about these things and you just assume that R has its default, so the default in R is a treatment contrast. So if you run this model, you set the treatment contrast. You don't set the contrasts, assuming you haven't heard about contrasts. You don't set the contrasts. It's just a treatment zone contrast. And then you want to interpret the effect of A in this model, and you get a 0. And maybe you assume that it's the overall effect of A, but in fact, it's just the nested effect. So this is a bit dangerous, the way R is set up, because it easily leads you to believe that there is no effect in this situation. So you just have the wrong belief about the data. So what about the effect of B? The effect of B, we again, interestingly, have to look at what A is coded as. A is coded as a treatment contrast as well. So A1 is the baseline. So the effect of B just tests the difference between the levels of B for factor level A1, the baseline. So this is a difference of 20 minus 10 is 10. And this is exactly what is captured here. The interaction term, then, you can say, so the main effect of, so A2, this A tests the effect of the nested effect of A. To obtain the interaction effect, you first have to take the effect of A, this is 0. Then we take the effect of B, that is 10. So this is the prediction without the interaction. Just considering the simple effects, you get the prediction that we are at 20 now. So the intercept, the intercept said 10, then there was an increase of 0, an increase of 10. And now the interaction test captures the difference between this prediction and what the data point up here actually shows. The difference here is 20, and that's where the 20 comes from. Okay. So this is not an ideal situation here. In some situations, it might be meaningful and useful. Maybe sometimes you want the situation that you want to test the nested effect of this and the nested effect of this. And in these situations, so it can be really useful. If you specify this here as the, if you specify B2 as the baseline level, then your main effect of A tests this nested effect of A within B2. Then your model can test whether there's a effect of word difficulty in reading, and then you can test the interaction, whether this is stronger than in search. So there are situations where this might be useful if you think about it, if you consider it closely. That's why I want to explain to you how this works in general, so you're flexible in using whatever contrast suits you, even in a 2x2 design or more complex designs. Okay, we can also use the generalized inverse to see what these contrasts actually measure. So I showed you by comparing the estimates to the figure, but we can also extract the contrast matrix, assuming a four-level contrast. This code extracts, so first summarizes the data such that each factor level just comes up once. Then it extracts a model matrix for A times B and stores it as a matrix. So we can have, again, this matrix that we saw before, A1, A1 to A2, A2, and B1, B2, B1, B2. These are the four conditions, X1 to X4, as we have called them in the other setup. And here we have the contrast matrix for the main effects and for the interaction. And what we can do now is we can compute the generalized inverse of that. And this gives us, from the contrast matrix, we can look at what hypotheses are tested by this contrast matrix. And we can see the intercept tests the average of A1 and B1. That's the X1 cell. Oops, I'm sorry. And the effect of A, the factor A, tests a nested effect. It tests this cell, so it nested within B1. So it tests A1 versus A2, both nested within B1. And the effect of B2 tests the difference between B2 and B1 nested in A1. Okay, so you can see here in the hypothesis matrix that these are nested effects. And then the interaction tests the whole interaction. This hypothesis matrix allows us to see that these are really nested effects, because if it would be a main effect, an average effect, well, no, we will see that how it looks like for an average effect in the next example. So how about some contrasts? They don't have a baseline condition, right? So we said if there's a baseline condition, this is coded as 0. So the effects of a factor are tested in the nested within the baseline condition. That was the case when we have treatment contrasts. So how about if there's no baseline condition? And then we can state this general thing when the 0 location of the other factor is the average of the contrast coefficients. So if we have if you have a centered contrast, then the main effects test the average effect across factor levels. I can read that again. When the 0 location of the other factor, because we always say the other factor, how the other factor is coded determines how you can interpret the one factor. So if the other factor is a centered contrast, that means the average of the contrast coefficients is 0, right? What we can do then is we can say that the main effect, the effect of factor A, tests the average effect across the other factor levels. Okay, let's again go in an example. Let's assume both. We had the situation. This is kind of then you get an ANOVA. We said both are some contrast coded, and we have factors A and B in the interaction. And now we see it back here again. These were the results that we also got in the ANOVA. And now we can say, if we want to understand what factor A tests, we think about how B is coded, because then it's an interaction. So we have to think about how B is coded. And the location 0 is not in a baseline condition, but it's the average of all of all the contrast coefficients. So the other in B, it's a 1 and a -1. That's some contrast. We learned that before. The average of 1 and -1 is 0. So that tells us that the factor A tests the average effect for level B1 and level B2. Let's go to the figure. So we want to know the effect of A averaged across levels of B1 and B2. So B1 and B2 are these two lines, and we want to test the effect of A from left to right. So how is the left side different from the right side? In this situation, and we can see, so it's here we have an effect of 20. In B2 we have an effect of 20. Here we have an effect of 0. So the average difference is so the average of 20 and 0 is 10. Okay, so the average effect here is 10. But so this is a bit tricky. I'm a bit mean here. This is a sum contrast. So the sum contrast doesn't give us the full difference. It just gives us half the difference, right? Remember that. So therefore, we get a -5 here instead of a -10. But apart from that, it just gives us the average effect, average across the different factor levels. I hope I'm not losing you. How about let's do it the other way around as well. What is the effect of B? The effect of B has to be, we interpret the factor B, we have to know how A is coded. A is coded as a sum contrast. Again, the location 0 is the average of the conditions, so we have to compute the average effect of B across levels of A. So we can compute the effect of B for A1, that's 10, and the effect of B for A2, that's 30. So the average of 10 and 30 is 20. Again, this is a sum contrast. So the sum contrast doesn't test the whole difference, but it just tests half the difference. So 20 divided by 2 is -10. And we can again extract the contrast matrix for this. By summarizing the data for each factor level, then extracting the contrasts with the model matrix for factor A and B and their interaction. And we can see this is the contrast matrix that we now have. We apply the generalized inverse to see what the hypotheses are. And now we can see, before we saw these nested hypotheses. So this condition for the treatment contrasts, X3 was compared to X1, and X2 was compared to X1 for factor B. But now with the sum contrasts, we see that these are not nested anymore. These are average effects. So factor A tests the average of 1 and 2 against 3 and 4. And the effect of B tests X1 and X3 against X2 and X4. Okay. This is a bit of, yeah. So just to remind you of the general rule, if an interaction is included into the model and you have the main effects in the interaction, the effect of each factor tests in the interaction tests its effect at the location 0 of all other factors in the interaction. Depending on where the location 0 is, this can yield either nested effects when you have a treatment contrast, or you can have average main effects if the other contrast is centered. This is the centering is mostly the case. And remember that I said in the beginning that I showed you these differences. I showed you these differences between contrasts for the simple two-factor example. We just a two-factor level example, just X factor 1 and factor 2. And I said that the intercept can represent different things. It can represent the baseline of the one baseline level, the other baseline level of the average. And I said in this simple example, it doesn't matter. But if the contrasts are centered, if there's a centered contrast, this means that the intercept captures the grand mean. And that's what we always want to have. We want that the intercept captures the grand mean, unless we have a specific other plan. But generally we want that the intercept captures the grand mean. Why do we want that? Because then the effects that we observe are the average main effects. Okay, so if all the factors in the design have a centered contrast, then we can simply interpret these effects. We can simply say A is the effect, the overall effect of A, B is the overall effect of B, just like in the ANOVA, main effects and interaction. But if we have a situation where the contrasts are not centered, where, like in the treatment case of the treatment contrast, where the contrasts are not centered and the intercept does not capture the grand mean, then suddenly we turn out in a situation where we have nested effects. A tests the nested effect and B tests the nested effect. So this is the general. This is the reason why I'm discussing these things in so much detail. So the general conclusion, if you're not sure about the details, you can simply say use centered contrasts if you want to interpret the effect of factor A as a main effect, as an average effect. What is the difference between the two levels, independent of B? And so if you want to interpret your effects as the average main effects, then you should use centered contrast, such as sum contrast, but also other contrasts are possible. Yeah, I hope I haven't confused you too much about this. If you're still awake, but it seems like. So we can go to more advanced stuff. So yeah, maybe so. So maybe we can. So is there a strong preference of whether we should? I'm not sure how much time. Maybe we can just start. I think we're getting forward quite quickly. So let's go to a 3x2 design, just as an example. So now we have in the mixed design function, we can simulate data. And now we have two factors, one with 2 factor levels and one with 3 factor levels. So 2 times 3 is 6. So we have to indicate. So we have to provide 6 condition means in this matrix M that we saw before. Then we do a bit of renaming of the factors and the factor levels, and So this is an example that is from my PhD, from a dissertation. We have, I said in the beginning that I studied mindless reading, so whether people pay attention to the text when they read. And the one general finding is that if you pay attention, so you're on task, that's the red dots here, then there's an influence of word frequency. So difficult, low frequency words take a long reading time, and high frequency words are fixated very shortly. But if you're not paying attention, these fixation durations are all the same, independent of the difficulty of the word. So this is the 2x3 design that I put up here. We again compute the summary statistic. Maybe we don't go into the details of the commands. You can have a look at them. So what we can do in the situation now, we can run, again, I'm using the AOV function. Sorry, maybe I should have a closer look at that. But here we are in an orthogonal situation, I think. So, oops, shouldn't make a difference. So if we use an AOV, we can get a main effect for mindless. For the mindless effect is not significant. So the difference between red and green is not there. We can have an effect of word frequency. So somehow word frequency plays into this result. And then we can test the interaction of mindless reading times word frequency, and there we have a significant interaction. Of course, from these results, we don't really know where these effects come from. So instead, what we can do, we can test specific hypotheses using linear models. Let's assume that we specify a treatment contrast for mindless reading, where we say the baseline is that we are on task, and the other condition is that we are off task. Then, yes? Yes? Exactly. A continuous, yeah, continuous. That is a very good question. So it depends on how you set up the study. Sometimes what people do is they have an experimental manipulation with high, low, or medium word frequency in one target location. So you're not looking at all words, and then you could have word frequency as a continuous variable, as a covariate. But you could also have an experimental setup where you have the same sentence, but one word is exchanged, and in one situation it's a high frequency word, once it's a medium, and once it's a low frequency word. So you could have more experimental control that it's really word frequency and not the position in the sentence or something like that. Okay. So this would be the case if you have an experimental design rather than a correlational design. And then you can have these situations where you have where you group that. Of course, you could also, so at least that's what some people usually do. But my claim here is not too much that this is the best procedure. I see your point that it could be useful to just use it as a continuum. I also sympathize with that view. I'm not trying to push forward the idea that this should be done in this way. It's just take it as an example, okay? Yeah, but it's quite standard. Let's say it like that. Whether it's good or not is another question. But you can. That was just the example that came to my mind first. I can think of something else as being the content of this. Okay, so let's assume for mindless reading we have a treatment contrast. And for word frequency, we do a sliding difference contrast. So we take the difference between low and medium and the difference between medium and high. So now let's run the model, mindless times word frequency. So how can we now interpret these regression coefficients that we get? So what do these different things test? We can now see that we have not one factor, not one main effect of word frequency, but we have two effects here. And we also have two interactions, and we have an effect of mindless. So let's start with the mindless effect. So how can we interpret the effect of mindless reading? So the difference between on task versus off task. First we know that we have the interaction included. So to interpret the effect of mindless reading, we have to know how word frequency is coded. Word frequency is coded as a sliding difference contrast. The sliding difference contrast has a mean of 0. So that tells us that the effect of mindless is the average effect of mindless reading across all word frequency levels. Okay. So overall, wait a second, when we are off task, we are 10 milliseconds faster than when we are on task. Okay, so when we go from on task is 0 to 1 off task, we have to go down to minus 10 milliseconds on the scale. So red is 10 milliseconds higher than green on average. So how about when we want to interpret the word frequency effects? So if we want to interpret the word frequency effects, we will have to check what the mindless reading condition is coded as. It's coded as a treatment contrast. So that means the word frequency effects that we have here testing the effect of word frequency in the baseline condition of mindless reading. So that's when we are on task. Okay, so that's the red line. So and then we can have both comparisons. We first compare 2 versus 1, medium versus low. And we see that this is from 250 to 210. That's a difference of 40. And this is exactly reflected here, highly significant effect. And then we see that the second word frequency is comparing 3 versus 2, high versus medium. And this is a difference from 210 to 200. And it's a difference of minus 10, which is not significant. Okay, so this is interesting here. We can have a design where our word frequency effect directly captures the effect when we are on task. And then the interaction tells us whether this effect is reduced in mindless reading. So how do we interpret the interaction terms here? So it's always a difference between on task and off task and how the word frequency effect changes. First, let's look at this effect 2 minus 1. So the effect of 2 minus 1 is medium versus low, and it's 0. The difference is 0 off task, and the difference is 40 on task. So the difference between 0 and 40 itself is 40. So this gives us the 40 here, and this is a significant interaction. We can see this line is steeper than this line. And then we can do the same for 3 versus 2, so high versus medium. We once have an effect of 0, then we have an effect of minus 10. The difference is exactly 10. Okay, so by having on task as the baseline condition, we can in one model get the word frequency effect in normal reading and the difference to mindless reading. So if these are the two effects that we hypothesized, in normal reading there should be an effect and this should be reduced in mindless reading. This could be one way to code it. But there are other possibilities. We can also say, which I personally find a bit less convincing, but could also do that. We could say we use a sum contrast for mindless reading. An effect coding, plus 0.5, minus 0.5. But now we do a polynomial contrast for word frequency because we want to really get the linear effect and want to test whether there's a quadratic effect. So if we do that, and we first look at the effect of mindless reading, then we have to know how the word frequency effect is coded. It's coded as a polynomial contrast that is centered. If it's centered, that means mindless reading tests the average effect of mindless reading across all word levels. It's again 10. So again, the same difference. So how about if we want to interpret the word frequency effects? Now we have to look how mindless reading is coded. Mindless reading has a centered contrast. So word frequency tests the overall effect of word frequency, averaged for mindless reading and mindful reading. And we can see the linear effect declines significantly, so minus 17. So there's a linear decrease across word frequency levels. And there's also a quadratic effect, which is positive, but it's not very strong. And then the interaction tells us, the interaction tells us what is the difference between these two linear trends. So there's a linear trend in the on task, and there's in mindful reading, and there's a linear trend in mindless reading. And the difference between these two linear trends is 35 and is significant, and the difference in the quadratic effect is not significant. Okay, these are two examples how you could analyze this situation. But there are more possibilities. It's just to illustrate some of the points that we have seen. Yeah, and then you could also do nested testing for this example. Let's say we use again effect coding and the polynomial contrast. So the coding doesn't change, but let's say, wait a second, we want to test the effect of mindless reading for the different word frequency levels. So the effect of mindless reading nested under word frequency. So we want to test whether mindless reading slows down reading when there's a difficult word and whether it speeds up reading when there's a high frequency word. And we can specify that here word frequency slash mindless, and then we get an effect of 40 here. So this is word frequency low. If word frequency is low, then we get the effect of mindless reading of 40. That's the difference here. 250 minus 210 is 40. If word frequency is medium, we get an effect of 0. That's the medium condition. And if word frequency is high, we get an effect difference of minus 10. That's this one here. So that's one way we can do the nesting. But we can also, and that's maybe more reasonable, we can look whether the word frequency effect, whether this is significant under mindless reading and mindful reading. So we can nest word frequency under mindless reading. And this could be really one of our hypotheses, that we say we expect the word frequency in mindful reading, but we expect that it's absent in mindless reading. And then we can see here have an effect of mindless when we are on task. So mindful reading, a linear effect of word frequency is highly significant with minus 35. But when we are off task, when we're not paying attention, the word frequency effect is exactly 0. And again, we can do the same for the quadratic effect. When you're on task, there's a slight positive quadratic effect that is not significant, and it's again 0 in the off-task condition. Okay, now you can start to use all of these capabilities to more complex situations, but that's the example that I wanted to show. So we have half an hour, so I could start talking about covariates if that's of interest. That would be the next step. Okay, let's do that. So the most simple case for analyzing a covariate is the so-called ANCOVA, the analysis of covariance. And now we can simulate data here. Note that now we have a within subject design because we have two variables that we simulate for each subject. So that's why we have a 2 by 2 assume a 2 by 2 design. So one is between subjects. We have two groups, but then we have two variables for each subject, and for that we have to specify a matrix of condition means. Yeah, we specify the means for each of these four conditions. Standard deviations can also be specified for each condition separately. And then we say we have a one factor with two levels for the between subject group. And we have a within subject manipulation with also two levels. So if we rename these variables, we end up with the following data frame. We have some group factor x, x1 and x2. So we have two groups of subjects. Here is the subject number. And for each subject, we have a dependent variable and we have a covariate. So this is kind of, we're using this within subject manipulation to generate data from two random variables for each subject that are correlated. So we assume a correlation of 0.4 here. So the covariate and the dependent variable are correlated. And we have some group difference as well. So what could this be? For example, the classical example for ANCOVA situations is that you have some training program. That's your group X, X1 and X2. One group gets a training, so let's say some cognitive training to perform a task. and the other group is the control group, and you want to see whether the training improves learning or improves performance on the task. But then you might have a covariate, which is, for example, IQ. So maybe by chance, the IQ of the people in the training group was higher than in the other group. So you want to control for the IQ differences between groups. So how would we start analyzing that? First, we would just want to know whether there's a difference between the two groups. So we can do effect coding for our factor X. We run a linear model that's just the same as if I would perform a t-test, and we find a significant difference. So the training group X2 has higher performance in the task than the control group X1. So this would be a simple kind of t-test between two groups condition. But now we want to control for this influence of IQ. Maybe this Q, maybe IQ, maybe by chance group 2 had higher IQ values than X1. Maybe that explains the better performance. What we can do to test that, so we have here the covariate is by entering this covariate into the as a predictor. In the very first session this morning, we already discussed that if you have a covariate, it's always a good idea to center the covariate, to subtract the mean. There's some exceptions from that we will discuss later soon. Let's see how long it takes. So we subtract the mean. We can simply do that by hand, or we can use this function scale, where we say center equals true and false equals and scale equals false. If you put scale equals true, then it gets a C transformation. If you put it to false, it's just centering. So these two commands are doing the same. And then now we want to control for this covariate, let's say IQ, when we test the effect of the group difference. So we enter this in one model just with a plus sign, and then we can look at the results, and we find that the covariate one step increase in the covariate leads to a performance increase of 2 points. Oh, sorry. And this is actually significant. However, when we look at the factor X, there's still a difference, but it's not significant anymore. So it was quite significant when we only tested X, but now when we consider the other variable, it's not significant anymore. And why is that? How can we imagine that? This is the diagram that shows the pattern of data. We can see that the green points are higher than the red points. That's what the t-test told us. But we can also see that this is plotted the dependent variable as a function of the covariate. We can see that overall with the covariate, there's an increase in IQ, increase in the performance on the task with higher IQ. So there's an increase of the scores with the higher values of the covariate. And due to this increase, and also we can see that the green points are further to the right than the red points. They are further to the left. So this simply means that the group X2, our training group, by chance had higher IQ values, and for that reason they performed better. But if you consider this influence of IQ, the difference between the lines, so the effect of X is simply the difference between these two lines, because they are parallel in this model. We don't have an interaction, so that means the lines are parallel. So this is just the difference between the lines. And for that reason, it's not significant anymore. If the groups would not differ on IQ, then the result might be different. One has to say, so this is already the ANCOVA. The ANCOVA is simply a model where you have a group difference and a covariate. But there's one prerequisite for the ANOVA that you can use it. You have to test whether there's an interaction between the group and the covariate. So you have to test whether the influence of IQ is actually the same in both groups. So you can specify that just by adding the star. And then you get this interaction term, which here is 0. So that's good. We can use the ANCOVA correction to test for the group difference. But if there's a difference in groups, then a difference in the slopes, if the interaction is significant, then you cannot perform this analysis of covariance correction. Okay. Okay, so this is classical ANCOVA, where we just want to see whether a group difference is stable when we control for the influence of some covariate. But there are also other situations where we might actually, so the interaction in this case, what the interaction tests is whether these two lines here, whether they are parallel. So if the interaction is 0, as is the case here, then these lines are perfectly parallel. But if the interaction is significant, it means that these lines are not parallel. One line is steeper than the other. And this is a situation that sometimes is of interest. We are sometimes interested in the differences between slopes. We already had this in the very first session, that there's an interaction between a group and a covariate. And we can simulate data for such a situation using the same mixed design command, but now we don't specify a fixed level for the correlation between the two groups, but we specify a list here where for each group you enter a correlation matrix. And in one group, let's assume there's a positive correlation between the covariate and the dependent variable of 0.6, and the other group is a negative correlation between the covariates. I can show you how the resulting data look like. So here, this plot on the left side is the data that we have that is resulting from this from the simulation. We have a covariate that varies between, let's say, 30 and 70, and we have a dependent variable, and we can see that in group X1 there's a strong increase of the dependent variable with higher values of the covariate, and X2 there's a slight decrease. So how would we analyze such a data? Let's assume, how would we analyze such a data set? Let's say we use effect coding for the factor x. So sum coding divided by 2, then this should be minus 0.5 and plus 0.5. And what we can do now is we can compute the x times the covariate, so x star covariate. What we get then is an interaction term, and this is significant. And this tells us that these two lines are not parallel to each other. We can reject the null hypothesis that they are the same. So they're really different slopes here. Moreover, we can look at the covariate that shows an overall average increase of 1.25 with each step of increase on the covariate, which is not significant. Now let's look at the x, the influence of x. This is minus 202 and is significant. That's a bit surprising. Why is such a large effect? Does anyone know why there's such a big effect estimate for the condition difference? We can remember the rule that I said previously. I said if there are two variables in a model and we have the interaction included, then the effect of one variable depends on the 0 location of the other variable, right? So for example, in the baseline condition for treatment contrasts. Here we have a covariate. The covariate has also a zero location. The covariate is 0 at the location when the covariate is 0. It never happens in the data, but there is a location where the covariate is 0. And what actually is going on here is that this group difference tests the difference between these two lines at the location where the covariate is 0. And that's all to the left here. This is 220 compared to 20, so that's a difference of 200. So this rule that the location of 0 of the other effect determines how you interpret the one effect extends to covariates. So your covariate is a continuous predictor here. And in this case, we have the same thing. And so we can say, based on this model, that we extrapolate that if you have, let's say, an IQ of 0, then you have a difference between the two training groups. Of course, this might not be a very reasonable result or interpretation, because we cannot tell what happens when you have 0 IQ. Or maybe it doesn't make a lot of sense to say that in the first place. But because the factor x was coded as a sum contrast, as the effect coding, the mean of that is 0, so it's centered. because of that, we could interpret the covariate as the average increase of the, so it's kind of the average of these two lines and how this increases, and that's 1.25. Now we can say maybe we are more interested in the average difference between these two groups, not in the difference at zero, at an IQ of 0, but at an average IQ value. What we can do to implement that, we just, because that's what we forgot, we could just center the covariate. We subtract the mean and then run the analysis again. We can see that the interaction term is exactly the same. So it's 3.5 here, 3.5 here. The covariate is 1.25. That's again exactly the same. But the value of for x1, so the 200 minus 200 now gets down to minus 27. And this is shown in the figure on the right here. So now we have the covariate centered. So the mean is in the middle of the distribution. And now this minus 27 just tests the difference between these two lines at the location 0. Okay, and this is a much more reasonable location to test the difference between the lines at the average instead of at some extreme point. So here we could now test whether there's an average difference between x1 and x2. However, we can actually make use of this feature here. So we saw that we can put the 0 point in a very extreme position, or we can put it in the middle. But maybe we can also put it in a different location. Maybe we can put it here to the left side or further to the right side. Maybe we have a hypothesis that if you have a low IQ, there should be a difference between groups. But if you have a high IQ, there shouldn't be a difference between groups. And this is actually something we can test in such models. And we again use the covariate and subtract the mean. But now we can add one standard deviation of the covariate. So we move everything a bit to the right. Now the 0 line is on the left. So we are now, the 0 line is at the location of, let's say, low IQ people. And we can do the same. We can take the covariate, subtract the mean, but now subtract one standard deviation of the covariate. Now we move everything a bit to the left. And now the 0 point is at values where for subjects with an IQ 1 standard deviation larger than the mean. And we have stored this as NL and nested under low IQ and nested under high IQ. And now we can use these covariates in our linear models, and we can look at the effect of X. And we can see in this case where we have said this is a low IQ condition, we can actually see that for people with an IQ 1 standard deviation below the mean, we have a difference of minus 66 points on the dependent variables, which is highly significant. But if we use this other covariate, so this one, where the 0 location is under high IQ people, we can see that under this condition, there is no group difference. So it's just a difference of 11 points, and it's not significant. So these are analyses that you can perform, but importantly, you should only perform this analysis if the interaction is significant. That's just a post hoc test if you have a significant interaction, but you can use this rule that the point null is that the effect of X depends on the coding of the covariate to test these specific nested effects. So it's an effect of factor X nested under low or high values of the covariate. Okay. What you can also do, you can nest the effect of the slope under one level of the factor. So what happens if we assume the treatment contrast, the factor X has a treatment contrast? So condition 1, x1 is 0 and 2 is coded as 0 and 2 is coded as 1. If we now run this with a centered covariate, we can see that the effect of the covariate has changed. So x2 is again this 27 that we saw before. The interaction is unchanged. But what is new is that the covariate now has a slope of +3. And the reason for that is, if you want to understand the effect of the covariate, we have to look at the x variable. So how is the x variable coded? And the effect of the covariate will be tested in the baseline level of x, because we have a treatment contrast. The baseline level has a 0. So that means that our covariate here, the effect of 3.0, tests the covariate in the baseline level of x, which is x1. So we get the red line. So this effect here captures the red line. Actually, we can also do a formal nesting of the covariate under levels of x, and then we confirm that the covariate under level x1 has a value of 3 and is highly significant. That's exactly the same value we observed here. And that the covariate under x2 is slightly negative, 0.5, and is not significant. So all of these concepts of nesting, of baseline levels versus average effects, they all extend to covariates. It's just the same. Just have to extrapolate these concepts to a continuous dimension. Are there questions currently? Or should I do the last bit?
I would have a question, because I noticed that what you were now explaining in one of our data sets, that the covariate is only significant for one treatment group.
Yes.
And then, okay, then we set the baseline for one group where it was significant, so that it looks more nicely in the paper as a storyline. But basically, is this then okay to report it just one-sided? Or would we also have to report that for the other treatment, it would not be significant, the covariance? So if I would recode.
You mean, yeah, okay. You mean this analysis with the treatment contrast, and then that you find a significant effect in one group, right?
Yeah, exactly. So that's significant for one group, but not for the other. Depending on which baseline I take, then
Exactly.
the covariate is significant or not. And then, okay, we did the coding of the treatments group so that we got the covariate significant for reporting that.
Yeah. So if you don't have a specific hypothesis about that,
yeah,
then you shouldn't do it. Then you should test the average effect. Okay. So generally, the general recommendation is always use centered contrasts. For example, sum contrast or effect coding. These, I mean, by default, R uses a treatment contrast, but that's often not a good idea. So if you, I am only showing this to you in the case that you have a very specific hypothesis. I'm sorry, thanks for the question. This is an important point. So you should only do that if you have a very clear hypothesis that the red line increases, but the green line doesn't. And if that's your hypothesis, then you can do this analysis and show the red line increases and the other one is significantly less increase or even a slight decrease. And you have both of these significance tests in one model. But if you're just interested in the effect of a covariate, and you don't have this a priori hypothesis, then you should definitely use the sum contrast and effect coding up here, for example, and then you report the overall effect of the covariate, and maybe the interaction where there's a difference. Okay, so
so you would suggest that we should not take the default.
Yes.
Okay.
Very good summary.
We should never take the default, but I guess a lot of papers are using the default, right?
And they don't know what they are doing, and they are reporting wrong effects.
Okay.
And I think that's quite a bit of a problem. Yes. And what I'm trying to say here, there are situations where these things make sense, but most of the time, maybe they are not so reasonable. But knowing when it makes sense and when it doesn't make sense and how to do what under what circumstances, that's what I'm trying to convey. Yeah, but you're completely right. The default should be avoided.
Good to know.
So if you don't have a specific hypothesis that this slope increases in x1 but not in x2, let's assume this is an influence of IQ on some task performance, and you just want to know whether IQ has an influence. If you use the default for the groups, you have the treatment contrast. That's the default contrast. Then you would, by default, get a nested effect here. So the covariate would give you the result for one group, but not for the other. And maybe by chance, this group has a stronger effect and shows a significant effect. But this is not what you're interested in. You're interested in whether overall there's an effect of IQ. And not whether in one of the groups there's an influence of IQ. Okay? Does that make sense? Not so much yet.
Mm-hmm.
Yeah.
I have another question. If we have really a control group, is it then a little bit better to take the default contrasts of R?
So yeah, if you have a control group, then there can be some situations where this makes sense. Yeah, if you have a clear control group. Mm-hmm. But even so it depends on your hypotheses in the end. Yes, it can be. There are situations where this is a reasonable thing. But then the question is whether you're interested in whether the IQ effect is stronger in the control group than it is. Still, you can ask, even if you have a control group, it might be the case that you are still interested in the overall effect of IQ and not in the effect of IQ in the control group. Yeah, but I agree. There can be situations where it makes sense. I'm not saying this doesn't ever happen. No. Mm-hmm. Yeah. Yeah. Exactly. You are completely right. What you can do is you can remove the interaction and test the effect of IQ. Yeah. Yeah, that's in correlational research, that's usually the way you do it. Yeah. In experimental research, some people sometimes tend to include the interactions from the beginning. Yeah. Okay, cool. I think we are at the end of time. Also, I mean, what I had next was just a level with a 4-level factor, but nothing changed in principle. Just how you can compute some slopes, nested slopes in that situation, and how you can have different contrasts for comparing the slopes between different conditions. So you could have a treatment contrast where each slope is compared to the baselines, to the slope of the x1 level, to the baseline level. So this is steeper than the red line. Or you could have, well, this is very quickly going over this, I'm sorry. Or you could have a sliding difference contrast where you compare the slopes of neighboring group levels. So you compare the slope of the red line versus the whatever x2 green line versus the green line, then the x2 versus x3, and then the x3 versus x4. So this logic of different comparisons directly extends to comparing different slopes. So this is so much steeper than this one, for example.